Orthogonal signals. In the previous video, we saw that one formula for energy of x of t is the area of the product of x of t with its complex conjugate. Using that formula, let's find the energy of x of t plus y of t. The complex conjugate distributes over a sum, which then is cross-multiplied with the other sum to give four separate integrals. The first integral is a formula for the energy of x of t, and the last integral is a formula for the energy of y of t. There are two terms remaining, which are the areas of cross products between one signal and the complex conjugate of the other. Hence, the energy of x of t plus y of t is the energy of x plus the energy of y plus two integrals of cross-product expressions. Signals x of t and y of t are said to be orthogonal when these cross-product terms equal 0. If one of the integrals of cross-products is 0, then the other must also be 0, proven by taking the complex conjugate of the top expression to obtain the bottom expression. So, signals x of t and y of t are orthogonal when the product of one signal multiplied by the complex conjugate of the other signal has area 0. As we saw, the energy of a sum equals the sum of the energies when the two signals are orthogonal. This property greatly simplifies our calculations when we deal with a sum of mutually orthogonal signals, that is, a group of signals that are all orthogonal to one another. The same property holds when calculating power. Here is an example of two orthogonal signals. They are orthogonal because they do not overlap in time, giving 0 product, that of course has 0 area. In that sense, orthogonality may be thought of as a non-overlapping of signals in some domain. Note the term energy signals. These are signals having finite energy. Energy signals have 0 power, so power is not a good measure for them. Here are another two signals that are orthogonal. In this case, they overlap in time, but their product has 0 area. See if you can verify that the energy of each is 1, and that the energy of their sum is 2, ignoring the fact that they are orthogonal. Power signals are signals having infinite energy and finite power, making power the best measure for comparison. One example of two orthogonal power signals are complex exponential functions of time having different frequencies. This leads us to conclude that two sinusoids at different frequencies are also orthogonal, since each may be expressed in terms of complex exponentials. That is true regardless of the values of their phase angles θ1 and θ2. Even when at the same frequency, two sinusoids are orthogonal when their phases are 90 degrees, or pi/2 radians, apart, such as a relationship between sine and cosine. In radio communications, this property makes it possible to transmit two independent signals using the same frequency bandwidth. One signal is carried by a cosine wave, and the other by a sine wave. In fact, in digital communications, any number of independent messages can be sent over the same frequency bandwidth without interfering with one another, as long as they are mutually orthogonal.